So I don't want to consume a lot of bandwidth for you guys. Probably you are at home. So I will stop recording, my camera, and then so hopefully it will be more smoother, the broadcasting. Now we are here, and then these examples are given here. The examples, you can see that it is very similar to what we have done in the lecture slide, right? In the lecture slide. So that lecture, if you have already, a similar thing that we have done, yeah, if you have done this or worked out this type of problem, it will be much easier for us to understand. It will be much easier for us to understand what we are going to do or what the question is asking in this tutorial. And most importantly, once again, we will be doing the number of moles, molarity, and especially number of moles. All right. So, okay, there. Okay, hold on, yeah. Edit PDF. There was supposed to be a pen here. No, I cannot see a pen. No. Okay, whatever, I cannot find it. So in my office computer, I also do not have other program to open it to it. Oh, I have the. Just a second. Okay, I can do it from here. I hope that you can see my screen now, right? And I think I can use my pen and pencil from here and then write on it so that it's better now. Okay, so jump into the almost half an hour gone. So jump into our question, first question. The first question is asking that the combustion of ethanol produces carbon dioxide and water. And we know that ethanol, if it is burnt in air means this way. We express it in this way because, you know, in the air there is oxygen. So first of all, is this reaction balanced? And the question is asking, if 100 gram of ethanol completed combustion, calculate the volume of carbon dioxide produced in liter. Carbon dioxide produced in liter at 100 degrees centigrade and at 1 atmospheric pressure. So quite many things to consider, isn't it? It is asking us quite many things. That if 100 gram of ethanol, have you ever seen ethanol? It is quite much similar to that what we are using for our hand sanitizing. For our hand sanitizer, we are using isopropanol, and ethanol, it looks alike. All right. Only the thing is, ethanol is used for hard drink, but isopropanol or methanol is very much toxic. It is almost poison that will kill people. So ethanol is not, I mean, it also, ethanol, there are so many cases, and that ethanol also does a lot of bad things to our brain and liver. But yeah, so, but those are instantly it will kill, and ethanol will kill you in long run if it is consumed regularly, whatever. Okay, so this ethanol, when it is burned in air means there is oxygen in the air. So if we look at this equation, do we see that the equation is balanced? Do you think that equation is balanced? First of all, of course, we have to balance the equation, right? We have to balance the equation. That is the most important thing, that the equation should be balanced. And now we see that here there are 2 carbon. Here there are 2 carbon. Here 5 hydrogen plus 1 hydrogen, 6 hydrogen. Here 3 times 2 is 6 hydrogen. And there is 1 oxygen plus 3 times 2, 6. So 7 oxygen is there. So now 2 times 2, these 2 plus these 2, it is 4. Oxygen is here, right? And then is 3 oxygen is here. So 3 times 3 plus 4, 7. So everything, all the elements on each side of the reaction, each side means, when I next time I will not repeat it, but when I'm saying each time, each side means be left and right of the arrow is all 7. All of them are balanced. Okay. All of them are balanced, the equation. So now, since the equation is balanced, we can comfortably say that 1 mole of ethanol, 1 mole of ethanol is reacting with 3 moles of oxygen and is producing 2 moles of carbon dioxide, right? 1 mole of ethanol is producing 2 moles of carbon dioxide when it is balanced. So this is the case actually, 1:2 reaction. So if it is 100 gram of ethanol, how many moles of ethanol actually? Because we do not care how many gram, how many weight, or how big it is, how good it is. All those things are counted is number of moles. Okay, the number of moles. What is the number of moles? So what is the molecular weight of ethanol? Can anybody tell me? What is the molecular weight of ethanol? How do you find the molecular weight of ethanol? Molecular weight of ethanol is carbon is 12 times 2, right? Carbon is 12 times 2. How do you know? We know from the periodic table. We know from the periodic table because carbon, each one carbon atom is 12, or carbon molecular mass is 12, and then there are 2 carbon atoms are there, so 12 times 2 is 24, plus hydrogen, let's say round up to around what is it called, round up or round down, whatever, what does it call? Okay, so it is 1.008, we just consider is 1, and it is 5 times 5, all right, times 5, plus oxygen is 16, and then another hydrogen is 1. So all together it becomes 24 plus 6 hydrogen plus 16, all right? So it is 46. It is 46, yeah. So some of us already know how to do it, but some of us maybe do not know. So that's why I just need to mention it here. So if 46, if we divide this 100 gram by 46, then we will go get the number of moles in ethanol. So 100 by 46 is 2.17 mole, right? 2.17 mole, right? 100 gram, 2.17 mole. So 2.17 mole of ethanol, how many moles of carbon dioxide will be produced? How many moles of carbon dioxide will be produced? Times 2, isn't it? Times 2, because 1 mole of ethanol, from the reaction we see, 1 mole of ethanol produces 2 moles of carbon dioxide. 2 moles of carbon dioxide it produces. I make it messy, yeah? But you know that it is 2. So 1 mole of ethanol produces 2 moles of carbon dioxide. So 2.14 will produce times 2, which is 4.35 moles, round up. Yeah, so 4.35 moles of ethanol, carbon dioxide will be produced. Now we know the number of moles, which is N. Number of moles is N. And now it is asking how many liters. How many liters will it be from that number of moles? And from the gas law, we know PV equals nRT. So V will be equal to nRT over P, right? It will be P, and we will just plug in this value. So N will be 4.31, R will be gas constant, and since it is atmosphere and Kelvin, of course, the 100 degree, we have to convert it to Kelvin. 100 degree will be 273. Always chemical calculation, never use degree, always use Kelvin. And how do we convert to Kelvin? We just sum up with 273, so that 373 Kelvin. All right, so 373 Kelvin, the temperature is 373 Kelvin, and then N is 4.35, R is the gas constant, and it, for this case, 0.08201, right? And P is 1 atmosphere. So from this case, if we calculate, we will find that the correct answer for this problem is answer A, 133 liter. Why so many faults now? Okay, so all right, so this is A is the correct answer. Question number 2, the initial reaction that occurs when a car airbag is triggered to inflate this is the equation. It occurs when, the car airbag is becoming inflated, when there is an accident or it gets bumped with something, the airbag comes out. So this is the reaction inside, and this nitrogen gas actually inflates the airbag. All right. How do I find the color? I want to change my color from green to red.
Sir, can you repeat the part where you got the 0.0821?
This one?
Yeah.
This is the universal gas constant, yeah? Universal gas constant. I think it is given here. If it is not, you can find it from anywhere. You can try Google it, universal gas constant, yeah? You will find it. Oh, here. Right? Yeah, this is one gas constant when it is in kilopascal. When we use kilopascal, so we use 8.31, right? But when it is atmosphere, it is 0.08201. It is not here given. Please refer to the lecture slide. It is given in the lecture slide.
Okay, thank you, sir.
Yeah. Okay. So this is the universal gas constant actually. Okay. So anyway, all right. So now it says that when 2 moles of sodium azide, this 2 moles of sodium azide reacts, which is in solid form, it will produce 3 moles of nitrogen gas. So from 2 moles to 3 moles it becomes, right? From 2 moles of sodium azide, 3 moles of nitrogen being produced. When 2 moles of sodium azide will be reacted, the total volume liter of gas produced by this reaction as measured at 32 degrees centigrade and 100 kilopascal is closest to, that means how many liter of gas will be produced, and then in this case nitrogen is only the gas, sodium is solid, S means solid, G means gas, L, when L in bracket means it is the liquid form, and AQ, when is AQ in bracket like this instead of G, if it is AQ here, we know it is aqueous solution. So since it is G, that means it is in gaseous form, this is liquid. And this question is saying that how many liter of gas will be produced. So that is totally, I mean, directly referring to this nitrogen, not sodium, because sodium is solid, nitrogen is gas. So again, the same thing, 2:3. So if 3 moles of nitrogen gas is produced, right? 3 moles of nitrogen gas is produced again from N equals 3 moles of nitrogen gas. So PV equals nRT. Please use the PV and nRT, the reaction, equation. And then from here, you will find the V, how much in volume. How much in volume the V will be. In liter, in liter, how much volume in liter you can find. And it turned out the same way that just now we do. It's the turn, it is 76 liter of gas, nitrogen gas will be produced. So 2 moles of sodium azide means how many gram of it? How do you find? 2 moles means how many gram? If we just multiply it with the molar mass of sodium azide, then we will find the mass of sodium azide from here, right? Question number 3. Everybody okay with this? Any question? Anyone? All right. Okay. If anybody has any question or it's not clear, please let me know so that I can discuss again. Question number 3 says 100 milliliter of 0.01 molar aqueous solution of calcium hydroxide will be absorbed. We will absorb carbon dioxide according to the equation. Calcium hydroxide, it's a lime, sometimes we call. So this thing is in aqueous form. Aqueous form means when it is dissolved in water. All right, when it is dissolved in water, then it will dissolve or absorb carbon dioxide from the air. So the carbon dioxide is maybe it's another good way, yeah, to reduce the carbon dioxide, because for carbon dioxide we have so many problems now, environmental problem. Actually, this is a one reaction. If anybody is pursuing chemical engineering and the environmental aspect, you will use this equation a lot. It looks simple, but it is not that simple. So this is one way to probably to save our environment, right? This is probably another way. So it says that 100 milliliter of an 0.201 molar aqueous solution of calcium hydroxide will absorb carbon dioxide according to the equation. The maximum volume of carbon dioxide in milliliter at STP that could be absorbed by the solution is what? how many milliliter of carbon dioxide this calcium hydroxide is capable of absorbing from the environment. So first of all, can I name call you and then ask, Brian, are you there?
Yes.
Looking at the first equation, how do you want to solve this equation? What the first thing that you want to look for in the equation?
Find the number of moles of calcium hydroxide.
Exactly. Thank you so much. So Brian, very good. You replied. I mean, correct answer. I hope that everybody also know this thing. So the correct answer is first of all, we should look what is the number of moles. The equation, the ratios of the reactant. Calcium hydroxide is one reactant, is another reactant. What is the mole of the reactant? So 1 mole of calcium hydroxide absorbs 2 moles of carbon dioxide, right? 1 mole absorbs 2 moles. So 100 milliliter of 0.1 molar aqueous solution will absorb how many moles? Is actually how many, what does it, how many moles is this? How many moles is this? Remember the equation that we saw first class, that N equals C into V, right? N equals C into V. So number of moles is equal to concentration into volume, right? So the concentration is 0.01, 0.01, and the volume is 100 milliliter, isn't it? Upati?
Yes, sir.
There. So should I use 100 milliliter?
No, sir. You need to convert it into liter.
Exactly. Thank you so much. So never use milliliter in any calculation. Yeah. In chemistry, we do not use centigrade, degree centigrade, and milliliter. In calculation, we do not use. Later, we can convert back to degree centigrade or milliliter, but in any calculation, liter and Kelvin is always used. So 100 milliliter divided by 1000 is equal to 0.1 liter. Right, 0.1 liter. So this is how we should find the number of moles. And it makes 0.001 mole. 0.001 mole of calcium hydroxide. So 0.001 mole will of course double of its value. That means 0.002, right? 0.002 moles of carbon dioxide will be absorbed, and 0.002 moles of carbon dioxide means how many milliliter of carbon dioxide? Oh, okay. So again, PV equals nRT. Right? PV equals nRT. This is a gas law that we use. So it is 0.002 for carbon dioxide moles, and this P and V should be at, what is that? At STP is given. At STP, we know that standard temperature and pressure. Standard temperature is 0 degrees, pressure is 1 atmospheric pressure. So we can find, or we can also find that is the V over Vm, right? Sorry, Vn equals V over Vm. Both way you can, whichever way you feel comfortable, you can do V over Vm. So Vm, we need to know the V. What is the V? We need to know. But Vm at STP is 22.4 liter. So if we just multiply this 0.02 times 22.4 liter, we will find the number of, volume of calcium, carbon dioxide. So in that way, it is going to be 0.0448, isn't it? 0.0448. 448, and it is in liter, right? it is in liter, and we have to convert it back to milliliter because it says in milliliter. So it have convert. So read in for example in exam, read the question first. If you says the milliliter and you just leave the question, I mean answer like that, you are losing 1 or 2 marks there already. So be careful. So 100,000 milliliter we have to multiply with this, and then it will be 44.8 milliliter. Question number 4. Anybody has any question, straight away ask me, okay? Don't wait for me to stop. Question 4 says the carbon monoxide can be oxidized to carbon dioxide. Of course it can be oxidized to carbon dioxide. What does oxidation means? Oxidation, oh, we haven't, okay, next week probably we are going to study. So carbon dioxide become oxidation, and then it's the oxidation number is increasing. Later we'll see what does it mean. So it becomes carbon dioxide. That means simply one oxygen is being added, but not always by oxygen it can be oxidized. It's about the electron. All right. So carbon dioxide is being oxidized, and then this is saying that 3 moles of carbon dioxide and 2 moles of oxygen are mixed together. This is the equation at first, just like Eric said, and Bhupati also said that we should look at the number of moles, isn't it? We should look at the number of moles, and this equation is balanced. As we can see, this equation is balanced, and by balanced equation, you see that 2 moles of carbon dioxide reacting with 1 mole of oxygen, and it is producing 2 moles of carbon dioxide, right? 2 moles of carbon dioxide it is producing. So here, if 3 moles of carbon monoxide and 2 moles of oxygen are mixed, when the reaction is complete, there will be how many moles will be left? Which, first of all, what are we going to look into it? Since the question is saying, what are we going to look into it? This is 2:1 reaction, isn't it? Yeah, it's simple. Mole ratio, exactly. We'll be seeing the mole ratio. But when this is the 3 moles of carbon dioxide and 2 moles of oxygen are mixed. So that means similar, clearly there is a reaction going on and the reaction is stopping at some point, of course, right? So when the reaction is going on, when the reaction is stopping, what we are looking? We are looking for limiting and excess reactant. Which one will finish up faster? Which one will finish up faster? So which will finish up faster or earlier is the limiting reactant, and which one is finished, does not finish up in the reaction, in the vessel it stays, in the reaction chamber it stays, because the other party has been finished already. So that is the excess, and that one, which one finished faster, is the limiting reactant. So how do you find the limiting reactant? We will divide the number of moles, available number of moles for the reaction with the coefficient of the balanced equation. So here 3 is the available number of moles for carbon monoxide, and the balanced coefficient of carbon monoxide is 2, right? For oxygen, it is 2 and it is 1, because nothing is there, so you consider it's 1. Not 0, it's 1. So in this case it's 1.5, and in this case it is 2. So which one is shorter or smaller will be the limiting reactant. It will finish up faster. Since carbon monoxide, this is for carbon monoxide, right? This is for carbon monoxide and this is for oxygen. So carbon monoxide 1.5 and oxygen is 2, the ratio of the mole to coefficient. So carbon monoxide will finish up faster. And if it finishes faster, that means there will be no carbon dioxide left in the solution, in the reaction mixture, because this is limiting reactant, right? So limiting reactant means all of it, all 3 moles of the carbon monoxide will be finished, right? All 3 moles of carbon monoxide. Oh, last week I think we were talking about the preparation of or producing of cakes, right? So that way, that if the smaller, the shorter one, it will finish up faster. So there will be no carbon monoxide left. Since no carbon monoxide left, so A cannot be an answer, B, C also cannot be an answer. Oh, no, sorry. A can be. Only C cannot be an answer. A can be still a viable answer, A, right? So C cannot be an answer. So C is not an answer. Now, if 1.5 of it is removed, how much of oxygen will be produced from 1.5? Since 2 mole produces 1 mole, 1.5 moles will produce how many moles of it? 1.5, sorry, not 1.5. Oh. This is what we needed to know to find out the, sorry, this one we needed to know to find out the limiting reactant, and now we have found already the limiting reactant. Now we are not considering this thing anymore. All right, this is just our info to get which one is the limiting reactant, and then we are done with this. Now we go back to this original question, that is 3 moles of carbon monoxide and 2 moles of oxygen. 2 moles of carbon monoxide produces 1 mole. 3 moles of carbon monoxide will produce 1.5 moles, right? This simple calculation, right? So 3 moles of carbon monoxide will produce 1.5 moles. Half of 3 is 1.5 moles of oxygen will be reacted with, and then the excess, that is 0.5 out of these 2. So 2 minus 1.5 is 0.5. So 0.5 moles of oxygen will be in the system left over. So D is the correct answer. Question number 5, it says that hydrogen and chlorine react according to the equation hydrogen and chlorine and 2 hydrogen chloride gas. Hydrogen gas, chloride gas, hydrogen gas, chlorine gas, and then hydrogen chloride gas is produced. So 3 moles of hydrogen and 2 moles of chlorine are placed in a vessel and sealed. When a reaction is complete, the vessel will contain, again, we have to see which one is the limiting reactant, because there are 2 reactants here. One is hydrogen, another one is chlorine gas. And we have 3 moles for hydrogen, and we have 2 moles of chlorine here. We have this available amount or number of moles. So which one is the limiting reactant? How do we find out which one is the limiting reactant? This reaction originally was balanced and hydrogen. Pupati says hydrogen. Okay, so this reaction was already, we have seen that this reaction is already balanced, right? This reaction, and then 3 divided by the coefficient of the reactant in the balanced equation. The balanced equation is already 1, and there is, in the balanced equation, there is only 1 in front of hydrogen. So this is coefficient 1, and for chlorine it is 2 over 1. Do you get where I get the 1 from? This is important actually. I want to know if it is okay for you. Vanessa, do you get where I get the 1? Hello Vanessa, are you there?
Yes, sir.
So you understand where I get this 1 that I'm dividing from with?
Yeah.
All right, good. Brenda, are you okay with that?
Yes, sir.
Arlene, how about you?
Okay, sir.
All right. So, Bella, you were typing something. Can you please just unmute and tell?
I was going to answer your question.
What is that?
I was going to answer your question.
Oh, so you understand where the one coming from, right?
Yes, yes.
Okay, okay, good. So we know that we are in the same boat. So we divided it and then we find that, of course, this is 2 and this is 3. So chlorine will be the limiting reactant here. All right. Chlorine will be limiting reactant. So the chlorine will finish up faster, or it will completely will be used up in the reaction. Now, since chlorine is the limiting reactant, the product will follow the limiting reactant mole ratio. Always remember, the product will always follow the limiting reactant. It does not matter how many tons of other reactant you give, is not 3. If you had given here 300, 3000, 3 million, it does not matter. The reaction will stop at after this 2 moles of chlorine is used. The reaction is stopped. The rest of the hydrogen will be there as it is. It will not be used up. Okay. Brian. Okay. Thanks for asking. Okay, let me write this equation first, or erase this one first. Okay, so now Brian, do you see the reaction hydrogen and chlorine, right? And it is producing hydrogen chloride. So this reaction is balanced, isn't it?
Yes.
Because 2 hydrogen here, 2 chloride on left, that means the reactant side. And we also have 2 on all of them. So we understand that there are 2 hydrogen and 2 chloride are there, right? So right and left are balanced. So since the right and left are balanced, we understand that there is 1 hydrogen in front and then 1 chloride in front also, right? So this one that I'm getting is actually this is called coefficient. This one that we have not written it, but we understand that there's 1 here. We call it coefficient. The coefficient, and in the balanced equation, same goes here. The coefficient for this reaction was 2. All right. For this reaction was 2. The coefficient for this reaction was 2. And this reaction is balanced as well. So this is 2 and there is 1 here and there is 2 here. So this is 2, these are balanced. Sorry, this is the coefficient. Same coefficient is this 1 and 1. So when they say that, okay, if I give you, Brian, that I'm asking you, okay, Brian, I'm giving you 3 moles of hydrogen and 2 moles of chlorine. You find out. So what you will do, okay, sir, give me 3 moles. Which one will be the limiting reactant? I know from this equation, this is the, balanced equation. This is 1:1 reaction. 1:1 means 1 hydrogen is to 1 chloride. So I call it, so we usually in chemistry, we call it 1:1. So 1:1 reaction and reactant 1:1. So I will divide by 1. If it was anything more than 1, just like 2, I divided here by 2, 3 by 2, so I get 1.5, right? 3 by 2. So I divide by 1, and then I know that this is 3 and this is 2. So 2 is smaller than 3. Since 2 is smaller, and 2 is for chloride actually, because 2 moles of chlorine I am given. So 2 is for chlorine. So since 2 is smaller than 3, so chlorine must be the limiting reactant. Okay, it is the limiting reactant. All right. Now, if I think we have some other problem like this, we will talk more. So first of all, we have to know the number of moles that we are using in the reaction? First of all, number of moles we have to know. For this reaction, we are using 3 moles of hydrogen, 2 moles of chlorine, and the stoichiometric ratio for this reaction is 1:1. This is balanced, or the coefficient. In many ways you can, or whatever way you want to call it, just call it, doesn't matter, as long as you understand what is the stoichiometric ratio, or the coefficient. So this one divided by this stoichiometric ratio, this number of moles divided by this, and then we find this is the number of moles. And 2 is for chlorine. So chlorine must be the limiting reactant. All right. Chlorine must be the limiting reactant because 2 is smaller than 3. All right. So if it is the limiting reactant, of course, chlorine will finish up faster than hydrogen. Hydrogen will not be finished up. And we understand that chlorine will finish up faster. How much chlorine will finish up? All of it. Because this is a limiting reactant, all of it, limiting reactant of all of it will be used up. So how much, if I ask anyone, how much of it will be finished? All right, how much of it will be finished? So we know that chlorine is a limiting reactant. So limiting reactant, all of it, 100% of the limiting reactant will be finished up or used up in the reaction. So 2 moles, all of these 2 moles that was provided with is finished up for this chlorine. And once it is finished up, these 2 moles, what will happen is how many moles of hydrogen will be finished, or how many hydrogen will it need to finish these 2 moles. And from the reaction, we see that it is 1:1 reaction. So if 1 mole of chlorine finish up, it will take 1 mole of hydrogen. If 100 mole of chlorine is used, it will take also 100 moles of hydrogen. If 1 million moles of chlorine is used, it will take exactly 1 million moles of hydrogen with it to produce or for the reaction to be finished. But since we have 2 moles of chlorine only, so 2 moles of chlorine will take 2 moles of hydrogen with it. So 2 moles chlorine will go 2 moles of hydrogen and then it's producing. But since we have 3 moles of hydrogen, 1 mole of hydrogen will be excess amount. It will be left. So 1 mole of hydrogen is left with it. Right. So this cannot be correct answer because chlorine will not stay, only hydrogen will stay. And now another, so there are 3 steps we are doing. First, find out the limiting reactant and see the stoichiometric ratio, the balance, see how much the ratio, so 1:1 ratio, exact same amount of hydrogen will be used in it. And afterwards, how much hydrogen will be left? 3 minus 2 is 1. So 1 mole of hydrogen will be left from this reaction. Now we are done. Oh, sorry, not hydroxyl, it is hydrogen. Water, hydrogen. So now the question is how much of the, our reactant side finished. Now go to the product side. How much of hydrogen chloride will be produced? Well, 1 mole of chlorine produces 2 moles of hydrogen chloride, right? 1 mole of chlorine produces 2 moles of hydrogen chloride. So 2 moles of chlorine will produce 4 moles of hydrogen chloride. So 4 moles and 1 mole of hydrogen. So this is the correct answer. All right. So is that okay now, Brian?
Yes. Thank you, sir.
All right. No problem. Yes, please. Chelsea?
Can you explain one more time? My internet was not good. Sorry.
Okay, no problem. So let me delete it first and then I go again. Okay. So this question is asking me that if you use 3 moles of hydrogen and 2 moles of chlorine, according to this reaction, how many moles of when the reaction is complete, the reaction vessel means where the reaction is occurring, that reaction vessel will have what it will be left with inside the reaction vessel, what is left with, right? We see, first of all, at the very beginning, we'll see that, okay, they gave me 3 moles of hydrogen, all right, 2 moles of chloride, no problem. Oh, sorry, not chloride, chlorine gas. So I have 3 moles of hydrogen gas and 2 moles of chlorine gas, all right, no problem. And I have to find out what is in the vessel at the end of the reaction. And I have this equation in front of me. So when I look at the equation, that the first thing I see whether the reaction is balanced. And I look at it and I see that reaction is balanced. I see that reaction is balanced. 2 moles of 2 hydrogen here, 2 chlorine here, 2 hydrogen here, 2 chlorine here, right, on the both side. So the reaction is balanced. Now another thing, I have to see what is in between the line, right? In front of hydrogen there is 1. In front of chlorine there is the 1. So this 1 and 1 is the stoichiometric ratio for this reaction. So the reaction is balanced in that way that 1 mole of hydrogen, when react 1 mole of chlorine, it will produce 2 moles of hydrogen chloride gas. All right. So it's 1:1 reaction. 1 mole hydrogen, 1 mole chlorine produces 2 moles of hydrogen chloride. So now, first of all, let's see limiting reactant. Limiting reactant. Because I have to find what is the limiting reactant. Only then I will find which one of them, because there are 3 moles of hydrogen, 2 moles of chlorine. I do not know whether all 3 moles of hydrogen will be used or all 2 moles of chlorine will be used, or some of these will be left in this vessel. So limiting reactant, how do we find it? We divide the limiting reactant with the stoichiometric ratio. So 3 moles of hydrogen, we divide by stoichiometric ratio, which is 1. So it is 3 for hydrogen, right? It's 3 for hydrogen. And for chlorine, it is, okay, it's 2 by 1. Yeah, 2 by 1. 2 is the mole of chlorine is provided with the me. Let's say that they have given me 3 moles of hydrogen, 2 moles of chlorine. So I was given 2 moles of chlorine and then the stoichiometric ratio is 1. So divided by 1, so it becomes 2. Hydrogen is 3, chlorine is 2. So which one is the lowest? Which is lower, smaller? Of course, chlorine, right? Chlorine is 2. Now we find out from our analysis that chlorine will be used up faster. Chlorine will be used up faster because chlorine has only 2 ratio, but hydrogen has 3. So hydrogen is bigger than chlorine. So chlorine will be used up faster. Right. Now we know already that the limiting reactant is chlorine. So all 2 moles, since it is limiting reactant, all 2 moles of chlorine will be used up in this reaction. So if 2 moles of chlorine is used, how many moles of hydrogen chloride will be produced? 1 mole of chlorine produces 2 moles of hydrogen chloride, right? 1:2 reaction. In this case, reactant to product is 1:2. Reactant to reactant 1:1. So reactant to product 1:2 reaction. 1 mole of chlorine is producing 2 moles of HCl. So now if I have 2 moles of chlorine and all these 2 moles will be used up because chlorine is the limiting reactant. So I will have 4 moles of hydrogen chloride. 1 produces 2, so 2 produces 4. Simple, right? So I will have 4 moles of HCl. in the vessel. And now all chlorine are used up because chlorine is the limiting reactant. So all chlorine will be used up. What about hydrogen? Since 1 mole of chlorine react with 1 mole of hydrogen, 2 moles of chlorine will react with 2 moles of hydrogen. So 1 mole of hydrogen will be left. All right. So 4 moles of chlorine, hydrogen chloride in the reaction, it will be there. And also that 1 mole of hydrogen that it could not react to it because the chlorine was finished, right, before. So 1 mole of hydrogen will also be in the system left. All right. I hope that clarifying. Is it okay?
Yes, thank you.
Okay, no problem. So question number 6, it says that a reaction mixture contains 0.6 mole of aluminium and 1.2 mole of magnesium dioxide was prepared. The mixture was heated until one of these reactants has been completely consumed according to the equation. What is the amount of the excess reactant at the end of the reaction? It's quite straightforward. It says that what is the excess reactant that it will stay at the end of the reaction. Now, first of all, may I ask, Noor Farah, are you there?
Yeah.
Okay, so looking at the reaction, what is the first thing that you want to investigate, or what do you understand looking at the first, looking at the reaction at the first time? What would you like to see in the, sorry? Hello?
Divide the given mole by the ratios.
Your voice is very low, weak. Can you speak a bit louder?
Hold on, yeah.
Yeah.
Hello, can you hear?
Yeah.
Okay. Divide the given mole by the ratios.
Oh, yeah. You have told me the inverse one. But first of all, I was asking you that if I look at the reaction, the first thing that I understand that this reaction is 4 moles of aluminium is reacting with 3 moles of magnesium oxide, isn't it?
Yeah.
Yeah. So this is the first thing that you should look at. Okay. When you look, okay, this reaction, okay, 4 moles of aluminium reacting with 3 moles of magnesium oxide. All right. So like this, okay. And yeah, thank you for giving me the advanced information that I should divide by the stoichiometric ratio. So 0.6 mole of aluminium I have, and I have 1.2 mole of magnesium dioxide. So what I'll do is 0.6. I want to know which one is the limiting reactant. So I will divide 0.6 with what? With 4, divided by 4 to find out the ratio, and it is giving me 0.15. And 1.2 divided by 3 is 3. So it is giving me 0.4, right? So which one is the limiting reactant now? Which one is the limiting reactant now?
Magnesium.
Yeah, who is it? All right, I don't know who talked, but thank you very much. No. Thank you for the answer, but which one is smaller? Which one is smaller?
Aluminium.
Yes, thank you. So I don't know who said magnesium, but it's okay that you said, no problem, because if you did not say, I would not stress on it. I would thought that everybody knows. So you know now why not magnesium is the limiting reactant, because magnesium, the ratio is 4 and the ratio for aluminum is 1.5. So 1.5 is smaller than 0.4, isn't it? 0.15 is much less than 0.4. So of course, aluminium is the higher, smaller. This is for aluminium. So aluminium 0.6 mole is for aluminium, right? So aluminium is smaller. That is why aluminium is the limiting reactant, not magnesium. Magnesium is the excess reactant. All right. How do you find the, once again, how do you find the excess and limiting reactant? Divide the given number of moles by the stoichiometric ratio of the balanced equation. So this is the balanced equation and this is the stoichiometric ratio. I mean the balanced equation. The equation is balanced and that's why we need 4 aluminium. We have to add 3 here so that the equation will be balanced. And now the question is asking 0.6 mole of aluminium and 1.20 mole of magnesium dioxide. So I have to divide 0.6 with the aluminium, divide aluminium number of moles by aluminium coefficient, divide magnesium dioxide moles by magnesium coefficient, and it is 0.15. So it is the limiting reactant. It is bigger value. It is bigger value. So it cannot be the limiting reactant. It cannot. Aluminium is the limiting reactant here. What is the amount of excess reactant at the end of the reaction? So excess reactant is magnesium, since it's 0.4. And how do we find the excess reactant? How much of the excess? We have 1.2 mole to start with. Magnesium, 1.20 mole of magnesium to start with. And then I have to deduct how much of the magnesium was used, or aluminium actually, how much of magnesium aluminium took from here. We should find out. So how do you find out how much it took? 4 moles of aluminium takes 3 moles of magnesium oxide, right? 4 moles of aluminium takes 4 moles of aluminium. I cannot write. Aluminium takes 3 moles of magnesium, MnO2, magnesium oxide. So 0.6 mole of aluminium, 0.6 moles of aluminium will take how many moles of magnesium oxide? 3/4 times 0.6 moles of aluminium, right? 0.6 moles of aluminium. So this is the 3/4 times 0.6, 0.45. 0.45 moles of magnesium oxide actually was used up, and out of this 1.2. So if we deduct 0.45 out of this 1.2, then we will have 0.75 left. All right. We will have 0.75 moles of magnesium oxide left. There is no answer for this here. It should be 0.75. Okay, there is no correct answer here, so it is 0.75. Now you know how to find out. Question number 7, it says that according to the law of conservation of mass, percent yield can never be greater than 100%. Of course, it cannot be greater than 100%. If you do not put 100%, how can you get more than 100%, right? Ammonia is manufactured by the synthesis of nitrogen and hydrogen as shown in the following equation. Again, first, when I look at the equation, I say, okay, it's 1:3 reaction, and 1 mole of nitrogen is producing 2 moles of ammonia, or 3 moles of hydrogen is producing 2 moles of ammonia. Both way you can describe it, doesn't matter. So if it says that 56 gram of nitrogen produces 34 gram of ammonia, what is the percentage yield of ammonia. Now, what is percentage of yield? Percentage of yield is how much product you have, how much product you have, how much product, suppose, I mean, 100% product. I don't know how, what else can I say? 100% product that you are supposed to have times 100%. So that is the percent of yield. Now this is quite tempting. A student all in this type of problem, student will always do what? 34 over 56 or something like that. 34 over 56 times 100%. They will try to find the number of percentage of yield. That would be totally wrong. Totally wrong. Question is 34 gram of ammonia you already have, right? 34.4 gram you already have in at your hand, but when you add nitrogen, so you have added nitrogen and 56 gram of nitrogen, and this nitrogen you did not get it free, you have to buy or you have to make it something like that, you have to produce it. So you are expecting a good fair return from it, isn't it? So you are calculating how much ammonia you can get. So if you calculate how much ammonia you can get out of this 56 gram of nitrogen, how do you calculate it? Oh, 56 gram of nitrogen means how many moles? If we divide by the nitrogen, right? Moles of molecular weight of nitrogen is 14. Nitrogen is 14. So 2 nitrogen is 28. If we divide by 28 gram per mole, we will get this 56 gram of nitrogen is actually 1.99999 something. All right, moles of nitrogen. So it's 1:2 reaction. 1 mole of nitrogen produces 2 moles of ammonia. So 1.999 will produce 3.999 something moles of ammonia. 3.99 moles of ammonia it will be produced. Right. So 3.99 moles of ammonia will be produced. Now 3.99 moles of ammonia. What is the mass number of 3.99 moles of ammonia? Is ammonia is 14 plus 1 hydrogen, so 15. If we multiply with 15 times 15, so it will be 59.99 something. 59.9999 something. So you were supposed to get 59.99 gram of ammonia, not 34. But you get 34 because it is a rare thing. It is almost impossible to get exactly 100% out of return, right? So we do not get 100%. So we expect that it will be a little less than 100%, but how much actually? 34 of 59%. So if we divide by 59.99 times 100% it will give us 49.9% of 49.9% of ammonia, percentage of yield. So that is 50%. We can just round it up to 50%. Question number 9. Sulfur trioxide is made from oxidation of sulfur dioxide and is represented by the equation. Sulfur dioxide, oxygen produces sulfur trioxide. What is the amount of sulfur trioxide obtained if the reaction starts with 16 gram of sulfur dioxide and has a yield of 75%? 16 gram of sulfur dioxide. The reaction is again 2:1 reaction. 2:1 reaction and 2:2 product, right, with sulfur dioxide. So sulfur dioxide, 16 grams of means how many moles? Sulfur dioxide is the molecular mass of sulfur dioxide 64 gram per mole. If we divide, we'll find is 0.25. 0.25 gram moles, sorry. 0.25 moles of sulfur dioxide. And then it is 1:1 reaction, because now 2:2 or 1:1, both way you can say. So if 2 moles of sulfur dioxide, it will produce 2 moles of sulfur trioxide. If 1 mole of sulfur dioxide, it will produce 1 mole of sulfur trioxide. If X mole of sulfur dioxide, it will produce X mole of sulfur trioxide. Exactly same thing it will produce. So if we add 0.245 moles of sulfur dioxide, I will have 25 moles of sulfur trioxide. So 0.25 moles of sulfur trioxide times molar mass of sulfur trioxide. Molar mass is sulfur trioxide is what is sulfur trioxide? Molar mass is sulfur dioxide is just now I divided by how? 64, isn't it? 64 plus 16 again. 4 plus 16, that is 80. Hold on, 32 times 48. Yes, 80. So if we multiply with 80, it becomes 0.25 is 20. So it becomes 20 gram of sulfur trioxide. We are supposed to, we could expect 20 gram, but now it is saying that out of this 20 gram, only 75% is being produced. So out of this 20, 75%, 7.75. 0.75, which one will be 15%? 15 gram actually. All right. Is it okay? But it say okay. All right. I hope that is okay. No question. Question number 10. Copper reacts with dilute nitric acid to produce nitrogen monoxide according to the equation. Copper, 3 moles of copper produces react with 8 moles of nitric acid, and it produces 3 moles of copper nitrate and 2 moles of nitric acid and water as well. When 6.75 gram of copper is added to 200 milliliter of 1 molar nitric acid, and the reaction allows to proceed to completion, 630 milliliter of nitric oxide is collected at STP. Which of the following is closest to the percentage of nitric oxide produced in the reaction that was actually collected? So, does anybody have any problem with understanding the question? Should I explain more, or I can just leave? All right. Yeah. Chelsea said explain, yeah? Okay. Actually, I was going to explain, but I wanted to know that you are sleeping or what. So when 6.75 gram of copper is added with 200 milliliter of 1 molar nitric acid. So from here, what do you understand? Can you find the number of moles? Because that is the only important thing, right? So can once again please tell with me, repeat after me that number of moles is important, not the milliliter or gram or volume. Repeat. Number of moles is important. So you look at the equation, I immediately understand that this reaction is 3 moles of copper react with 8 moles of nitric acid, and it produces, because it says nitric oxide, it is only our interest, it produces 2 moles of nitric oxide. Right. and it say now this says that 6.75 gram of copper is added to 200 milliliter of nitric acid. First of all, if I add this much of copper and nitric acid, how much of nitric oxide, NO, I was supposed to get? How can I find this one? Of course, we have to convert it to moles. 6.75 gram of copper means how many moles? 6.75 copper. Okay, 6.75 moles. Gram of copper means 0.1. We have to divide. You have to divide it by molar mass of copper, which is 63.5, if I can remember correctly. Or you can please refer to the periodic table. That is, you can find it anywhere. Periodic table of elements. Okay, so if we divide by the molecular mass of copper, that is 63.5, and we will get is 0.1 mole of 0.06 moles of copper. What about nitric acid? What about nitric acid? N equals C into V once again, and we have to, V means volume in liter, but it is in milliliter, so you have to convert it to liter. How do you convert it? You just divide by 1000 milliliter, so it becomes liter. So N equals C into V, because of this it is a solution, and from there we find the number of moles for nitric acid in 200 milliliter of 0.1 molar is actually 0.2 mole, right? So it is actually 0.2 moles. 0.2 moles. Okay. So now, which one is limiting reactant? You have to find out which one is limiting reactant. Don't just jump to the conclusion again. You have to see first. You have to find out limiting reactant in the reaction. So which one is the limiting reactant? Can you find? How do you find it? Who do I ask? Brian, can you tell me how do you find the limiting reactant here? No pressure, no marks deduction. I will not also scold you. No problem. But I'm not here.
Is it to divide the number of moles with the original number of moles from the balance equation?
Exactly, yeah. So the number of moles we find 1.106, and for here nitric acid we find the number of moles is 0.2. So I will divide this copper with 3. This is the stoichiometric ratio, the coefficient, and nitric acid by 8. I will divide by 8. So which one is smaller than 0.106 by 3 is 0.035, and then here it is 0.2 by 8 is 0.025. So since it is 0.25, the ratio, it is nitric acid is the limiting reactant. So this is the limiting reactant. So all these 0.2 moles of nitric acid will be finished up, but out of this 0.106 mole of copper, it will be left over in the solution. Okay. So actually, we have found 630 milliliter of nitric oxide or NO gas. It is actually not laughing gas. I don't know whether you know or not. So it's a laughing gas, and this, okay, so how much actually we are expecting if we have 0.2 moles of nitric acid, how much of nitric acid and nitric oxide can be produced out of this 0.2 moles? Here we see that it is 2:8, 8:2 reaction, right? 8:2 reaction. That means 8 moles of nitric acid, HNO3 produces 2 moles of nitric oxide gas. So 0.2 moles of nitric acid will produce how many moles of nitric oxide? So it will be 2/8 times 0.2, and that will produce the nitric oxide gas. 2/8.25 times 0.2 is 0.05. 0.05 moles of nitric oxide will be produced. All right. And if we want to know the mass, or this is the number of moles and it is an STP. So now you have to convert it back to PV equals nRT. PV equals nRT. From there we will find the volume of the gas of the nitric oxide, and then we can divide this 630 over the volume that I will get from here times 100%. So I will get it to some extent. And from here, the answer is actually 56%, right? So 56% only is produced. 630 milliliter is actually 56% of what it was supposed to produce. Question number 11, it says that gravimetric analysis usually involves the following 4 procedures: filtration, drying, precipitation, weighing, and for the correct answer is all 4 of them. 1, 2, 3, 4, all of them. And it should be in a sequence, right? So the gravimetric analysis will go for the first one is precipitation. Precipitation. We have to precipitate it out from the reaction first, and then we have to dry. All right. We have to filter it out from there. So it's 2. Number 2. Then we have to dry. 3. And then we have to weigh it. 4. So 3, 1, 2, 4. 3, 1, 2, 4. B is the correct answer in that way. The sodium chloride content of a 425 gram of baked beans was determined as follows. The chloride ions in 50 gram of the baked bean were precipitated as silver chloride. The mass of the precipitate was 1.051 gram. The amount of sodium chloride in the original can was closest to. How do you find it? First of all, what is the information given? The sodium chloride content of a 0.625 gram. 625 gram of beans. Okay. So total bean is 625 gram. And then the chloride ion in the 50 gram of the baked bean, we have taken 50 gram out of it. 50 gram out of it, and then we treated it with silver chloride, AgCl, to precipitate the sodium chloride as silver chloride, right? So we treated it with silver nitrate and then produced silver chloride. The mass of the precipitate was, whichever came out from the solution, was 1.051 gram. That we saw, it was 1.051 gram. The amount of sodium chloride in the original can was closest to what? In the whole can, how much is the total amount of sodium chloride? So now gravimetric analysis, we have to understand that silver and chloride is 1:1. That means in the silver and chlorine, silver chloride, right? So this is silver and this is chlorine. So 1:1, one silver ion, one chloride ion. They produces one silver chloride ion molecule. So 1.0501 gram that has been produced. We have to find out what is the mass, molar, number of moles of silver chloride. What is the number of moles of silver chloride in 1.051? So if we just divide it with the number of moles, if we just divide it with the number of moles with silver chloride, we will find the number of moles, mass of the silver chloride. The mass of silver chloride is 143.4 gram. So 105 we divide by 143.4, and that's how we get 0.007 733 moles of silver chloride. Another special or interesting thing is silver chloride. In sodium chloride, it is also 1:1. Okay, so just silver and sodium are exchanged. The chloride are there already. So since it is 1:1, it will be 0.007 moles of silver sodium chloride as well, right? It will be 0.001 silver chloride as well. Sodium chloride and silver chloride, right, is 1:1. That means 1 mole of sodium chloride is equal to 1 mole of silver chloride produced. Now, so that means this is the same number of sodium chloride, number of moles of sodium chloride as well, 0.0077 moles of sodium chloride as well. So 425 baked. Now we go back to this 425 baked. Okay, if in 50 gram, that is this much, 0.0077 mole, 773 actually, 77 mole in 50 grams. So how much will be in 425 gram, right? 425 times 0.0077 moles by 50. So this is how we will find the number of moles of sodium chloride will be in the solution, 0.0623. Question 13, it says that the amount of sulfate in a fertilizer was determined by gravimetric analysis by adding excess barium chloride solution. Highly insoluble barium sulfate was produced. which was filtered out, washed and dried. If the manufacturer's level states that the concentration of sulfur in the fertilizer is 11%, what should be the approximate dry mass of barium sulfate precipitate produced if the mass of the fertilizer sample under analysis is 1 gram? The amount of sulfate we have to determine, and it was precipitated out with as a barium sulfate by adding barium chloride. Okay, in the salt, the fertilizer, aqueous medium of the fertilizer, we added barium chloride solution. So barium sulfate was produced, and then this barium sulfate was analyzed, produced, and then filtered out, and then it was dried and then weighed. So it shows if the manufacturer's level states that the concentration of sulfur, so if the manufacturer says that, okay, 11% of the fertilizer is sulfur, whether they're saying truth or not, right? If you have garden at home, or if you do gardening or some plants in the vase, so maybe you probably put some fertilizer sometimes, so you can check in that way too. 11%, the manufacturer say 11% weight by weight percentage fertilizer is there. So whether they are saying the truth. Now, how do you solve this one? First, we have to see that barium and sulfate is producing that barium and let's say 2+ and sulfate 2- is producing barium sulfate. This is how barium sulfate is produced. So that they are bivalent. They are bivalent, and here. So mass of only one gram of the fertilizer sample was taken. 1 gram of fertilizer sample was taken, and it says that 11% of the sample in that fertilizer is sulfur. So if 11% out of in 1 gram, that how many percentage will it be there? Or 11% of 1 gram is how many gram is there? 11% of 1 gram is how many gram? 0.11, right? Gram of fertilizer. So 11% fertilizer means 0.11 gram of fertilizer mass of sulfur should be in the solution, in the sample. So number of moles of sulfur in that 0.11 gram. All right, so we have to find out the number of moles, because we are doing the backtracking, right? Because there is nothing else given, only barium sulfate is given from here, and we see that barium and sulfate from here, that 1:1 barium and sulfate in this reaction, and sulfur is whatever is only 1. Sulfur is 1, although there are 4 oxygen is there, but sulfur is only 1, right? Sulfur is only 1. So from there we understand that 11% of, when it is saying that 11%, so barium sulfate, we have 1 gram of the barium sulfate. So in that barium sulfate, how many gram of sulfur is there? So from there we can backtrack and find out how many moles of sulfur in the actually sulfur solution. So 0.11 gram of sulfur means how many moles of sulfur. And from there we can find 0.11 by 32 moles. If we divide gram per mole of sulfur, and it is we have to find out the number of moles sulfur. It is actually, it is given us that 0.343 times 10 negative third. Okay, so whatever, I am not going to write, you understand what I'm saying. And since sulfur, this is for sulfate ion. Sulfate ion, 11% sulfate ion. In sulfate ion, whatever number 3.43 times 10 negative third number of moles. So in this mole, there is only one sulfur as well, isn't it? In one sulfur. So the number of moles of sulfur will exactly be the same. This is the number of moles of sulfur as well. Okay, number of moles of sulfur as well. So if sulfate ion is precipitated as barium sulfate, so sulfate barium sulfate is exactly the same ratio. Number of moles is same. Barium sulfate, you have seen it here, is one sulfur in one barium sulfate. So 1:1. The production of this compound is 1:1 as well. One barium is one sulfate. So now is basically this is the moles of sulfur we have all together, right? We have all together. So from there, if we just multiply with the number of moles with barium, molecular weight of barium, which is 233 times 4 gram per mole, so that we will find is 0.8 gram of sulfur actually in the solution, in that fertilizer. 0.8 gram of sulfur in the fertilizer. Okay, question number 14 and 15. I finish it faster because it's almost 4. The percentage by mass of sodium ion in the form of sodium chloride is a particular brand of dry biscuit was determined using gravimetric analysis. A 3.65 gram sample of biscuit was ground into powder dissolved in water and filtered. Excess silver nitrate was added to the remaining solution and silver chloride was precipitated. The precipitate was collected, washed and dried. Its mass was found to be 0.241 gram. 3.6 gram of sample of biscuit was treated with excess amount of silver nitrate. And then the silver chloride was found. The precipitate was collected, washed, and it was found that the total was 0.241 gram. So this is what? 241 gram of silver chloride, AgCl, right? AgCl. It is silver chloride. And in silver chloride, actually, it is 1:1 silver chloride, isn't it? 1 mole, 1:1 ratio. If 1 mole of silver ion is there, silver ion and chloride ion. So if 1 mole of silver ion is there, 1 mole of chloride ion will be there as well. Oh my God, my throat is so dry. So 1 mole of silver and 1 mole of chloride will be there, and 0.241, same like actually the previous problem that we just now solved. 2.241 silver chloride means how many moles of silver chloride? We have to divide by the silver chloride number of moles, and it is 100. Silver is 107.87 plus chloride is 35.5, so 143.37. 143 actually, 143.37 gram per mole. So we will find the number of moles from here, and the number of moles is 1.6 times 1.68 times 10 negative third. Negative third. This is the number of moles. The good thing is that this silver chloride is the exactly same number of moles of chloride into the silver chloride. So 1:1. Exact number of chloride ion will be there inside. And then sodium chloride is also sodium is to chloride. So exact same amount of chloride will be in sodium chloride, so that we can find the number of moles is same. So the number of moles is here in the sodium chloride is same thing, and we will find the number of moles of sodium. It says the sodium, isn't it? How much of the sodium is there? So 1.68 times 10 negative 1.68 times 10 negative third times 22.9 or 23, you can say, gram per mole. It will be the mass of sodium, and that is equal to 0.0387. 0387 gram of sodium. So this much is in how many gram of sample? 3.85 gram of sample. 3.85 gram of sample. Actually, this means how many percentage? What is the percentage? Right? We can easily find out. Times 100%. So it is actually 1.06% of sodium ion in the biscuit. B is the answer. Question number 15, it says that the calculated percentage by mass of sodium chloride is lower than stated on the label of the packaging. This may be due to what? Incomplete precipitation of the chloride ion, inadequate washing of the precipitate, the precipitate not being dried to constant mass, or the precipitation of another unknown anion of the silver. So all those are, this is not the correct one. These two looks good, but the most important and most problem is incomplete precipitation. That means the chloride, when we precipitated, the chloride is not 100% precipitated. That's why it is less. It shows less than what it is on the packet. It is written on the packaging, right? So this is why it took so long today. And please go through this question. This exactly very much similar to what just now we talked. And I hope that you can solve. If you have problem, I am okay anytime to come and talk again. All right. Please let me know when it is, if you have done it or if you cannot see. And this is it for today. I know that some of you may have another class.